acredito que a maioria do pessoal já está chegando mais na horário. Vamos começar então com a palestra do Dr. Rangaraj, Rangayyan, e eu vou fazer uma pequena introdução ao currículo dele. Bom, o professor Professor Rangaraj Rangayyan is a professor of electrical and computer engineering and an adjunct professor of surgery and radiology at the University of Calgary, Alberta, Canada. He received the Bachelor of Engineering in Electronics and Communication in 1976 from the University of Missouri at the People's Education Society College of Engineering, Mandia, Karnataka, India, and the PhD in Electrical Engineering from the Indian Institute of Science, Bangalore, Karnataka, India in 1980. His research interests are in digital signal and image processing, biomedical signal and image analysis, and computer-aided diagnosis. He has published more than 150 papers in journals and 250 papers in proceedings of conferences. He has been recognized with the 1997 and 2001 Research Excellence Awards of the Department of Electrical and Computer Engineering, the 1997 Research Award of the Faculty of Engineering, and by appointment as University Professor in the period of 2003 to 2013 at the University of Calgary. He is the author of two textbooks, Biomedical Signal Analysis from Wiley published in 2002, and second edition in 2015, and Biomedical Image Analysis from CRC in 2005. He has co-authored and co-edited several other books, including Color Image Processing with Biomedical Applications of SPI in 2011. He has been recognized with the 2013 IEEE Canada Outstanding Engineering Medal, the IEEE Third Millennium Medal in 2000, and elected as Fellow IEEE in 2001. His Fellow of Engineering Institute of Canada in 2002, Fellow of American Institute for Medical and Biological Engineering in 2003, Fellow of SPI in 2003, Fellow of Society for Image Informatics in Medicine 2007, Fellow of Canadian Medical and Biological Engineering Society in 2007, and Fellow of Canadian Academy of Engineering in 2009. The title of the conference is Detection of Architectural Distortion in Prior Mammograms. Please, Professor.
Bon dia. Welcome to the seminar and good morning. Thank you for coming so early. In this talk, I will present a series of projects done by my students and collaborators for computer-aided diagnosis, but in particular a sign of early breast cancer or early stages of cancer known as architectural distortion. I'm with the Department of Electrical and Computer Engineering at the University of Calgary, and this project has been conducted in collaboration with Dr. Desertel, who was a radiologist with the Screen Test program, which is the breast cancer screening program in Alberta. First, I would like to give you an introduction to the nature of the problem, and then show a series of methods that we have developed to address this particular issue. Some of these statistics are a little old, but they still indicate the seriousness of the problem. In Canada, the lifetime probability of developing breast cancer is said to be 1 in 8.8. And the lifetime probability of death due to breast cancer is 1 in 27. 1% of all women live with this disease, and to assist in early detection of breast cancer in the general population, there are screening programs instituted by many countries and many provinces. In Alberta, there is a screening program, which I mentioned, and screening mammography has been shown to reduce mortality rates due to breast cancer substantially by up to 30 to 70%, depending on the study and the region of the world where the study was conducted. The signs of breast cancer that are visible in mammography are masses, calcifications, bilateral asymmetry, and architectural distortion. Now, this is a digitized version of a screen film mammogram. A mammogram is a two-dimensional projection image of the breast. Nowadays, the images are taken directly in digital format, but when we prepared this database, the images we got were on film. So we had to scan them with a high-resolution laser scanner. In a screening population, women in a certain age group, such as 50 to 70 years typically, as in Canada, are invited to participate on a voluntary basis. The women are asymptomatic, meaning they don't have any signs of breast disease. And they are invited to get mammograms done once every 2 years. If anything suspicious is found, then the woman is asked to come back for further examination. In a screening population, a large percentage of the women who are participating will not have any breast disease at all. More than 95%, could be 96% typically, would be normal, and they would be simply asked to come back in 2 years. Only about 1 in 200 women screened in a general screening population will be found to have breast cancer. So the radiologists who are working in a screening program to analyze mammograms would go through a large number of normal cases, such as this image, where there is no sign of any breast disease. And in perhaps 0.5%, 0.5%, they will find signs of breast cancer. In about 2% of the cases, they may find some signs of other breast disease. The most commonly encountered signs of breast disease are masses. A mass is a lump of high-density tissue in the breast, and if it is malignant, related to cancer, it is typically referred to as a tumor or a malignant tumor. Calcifications are deposits of calcium in the breast that may be due to benign disease or cancer. Bilateral asymmetry, is asymmetry in the pattern or texture of the fibroglandular tissue in the two breasts, the left and right breasts of the same person. And that requires comparative analysis of the two images. Now, we have previously proposed methods for detection of masses, calcifications, and analysis of asymmetry. And there are many, many papers in the literature on these topics. The fourth sign listed here, architectural distortion, is not very clearly defined in the literature and in the textbooks. And even the definitions given indicate a pattern that is difficult to observe and detect. And there have not been many studies on this topic. So we have concentrated for the past 10, 15 years on this particular problem. So here is an example of a mass. I have taken an image where the mass is not very easy to see. It's this little high-density region, which is noted as a bright or hyperdense object, and it is due to breast cancer causing increase in local density, or referred to as a desmoplastic reaction. Calcifications may be easier to see when they are superimposed by low-density breast tissue, such as here, but even then they could be difficult to see if they are very small. When you zoom, you see these little dots, white specks of deposits of calcium, and depending on the spatial distribution, the density, and the morphology, they will be determined to be due to benign disease or breast cancer. But when calcifications are superimposed by dense breast tissue, remember that mammogram is a projection of the breast. So there could be calcifications here, there could be dense tissue here, and you see superposition of all these tissues along the path of propagation of X-rays. If the calcifications were to be here, they would be very difficult to see. So we do need image processing methods for the detection of masses and calcifications. Bilateral asymmetry, here we have the left and right mammograms of the same person. You see a large dense region here but not here in this corresponding part of the other breast. So that is the reason for suspicion. Then further detailed analysis would have to be done to recognize or to understand why exactly this is happening. Many algorithms have been proposed, and I have collaborated with Dr. Paolo Mazzacini, Jesuit Marquez at the University of Sao Paulo, and Ribeirão Preto, and we have published a few papers on this topic for computer-aided diagnosis. Dr. Paolo Mazzacini, Jesuit Marquez will talk about CAD, C-A-D, or computer-aided diagnosis later. But there are many papers in the literature applying these methods to mammograms and other images. And in particular for CAD of breast cancer, it has been shown that CAD can increase the number of cancers detected substantially. It can also help in detecting early stage malignancy. With breast cancer, the earlier you detect the cancer, the better the prognosis for the patient. Unfortunately, there is a price to pay. The recall rate increased from 6.5 to 7%, 7.7%. Even in regular mammography, even in any clinical test, there will be a small percentage of false positives, false alarm. The patient or subject will be asked to come back for more tests. That is called recall. And then it may be determined that those subjects, some of them will not have any disease or do not have any disease. So the test can be said to have been a waste later on, but before the test was conducted, there was some doubt. So this is known as recall rate in the screening program. How many women will be asked to come back for more tests? The more the tests you do, including insertion of computer-aided diagnosis methods, the more the chance of false positives, and that is a small price to pay. Still, with the commercial systems and other systems available for the screening programs for breast cancer, 50% of the cases of architectural distortion were missed, according to some studies. So we concentrated on this problem. Why is it that the other methods are not addressing detection of architectural distortion? A method to detect calcification or a method to detect masses will not be able to detect architectural distortion. It is different. So for each pattern, each sign of a disease, you need a specialized image processing and pattern analysis method. Now yesterday, Dr. Leticia Ritter talked about various approaches for image processing and pattern analysis. For each sign you want to detect for each disease, we need to specialize the algorithm and then put them all together when you want to have a full system. So we concentrated on architectural distortion. This is said to be the third most mammographic sign of non-palpable breast cancer. Cancer or tumor or mass that cannot be felt by physical examination. The normal architecture of the breast is distorted. Now that is the definition given in the textbook, and it doesn't help. It is simply architectural distortion. You just play with the words and change. So we were a little disturbed at the beginning when we referred to textbooks and wanted to know what is architectural distortion, but there was not enough information. It is also said there is no definite mass visible. This is not a mass. There is no dense region or a nodule. Only distortion. In most cases, there are speculations radiating from a point. I'll show examples later. You may be able to see here, but it's difficult. And there could be focal retraction or distortion at the edge of the parenchyma. So to understand this, we went to Dr. Leo Desatel, our colleague from radiology, who has decades of experience in screening mammography, and he drew these pictures. Now remember that a breast is compressed to obtain the mammogram, and the mammogram is a projection image. So there will be multiple layers of breast tissue, and they will all be superimposed onto one plane of the mammogram. So there could be some ligaments here, some ducts here, tumor here, calcification there, they will all be superimposed. If you take a normal part of the breast tissue, a small part, you may expect to see parallel lines of tissue like this. Now they won't run parallel forever. Breast tissue converge towards the nipple. The ducts that provide milk send the milk towards the nipple, and the supporting structures also have similar orientation. So there is preferred orientation and a converging pattern of tissues in the breast towards the nipple. But if at a point where you expect the breast tissue to be going this way, you see breast tissue going somewhere else, that is distortion. So underlying pattern could be normal breast tissue in a small part of the image, and then there could be spicules radiating from all directions, or in all directions from a focal point, but there is no tumor here. Malignant tumors could have spicules, but there is no tumor here, only spicules. And they are superimposed on normal breast tissue. Sometimes there could be focal retraction, some tissues would be pulled, sometimes there could be an incipient mass that pushes the tissue, creating convex patterns or concave patterns, and spiculations are almost straight line patterns. So here's an example. Now that is a schematic drawing, it's easy to see, but in a real mammogram, it's not so easy. So here is a situation, a normal mammogram. The breast tissue is converging towards the nipple. If you take a small part here, the breast tissue will be in parallel lines. I'll show more examples later. In this image, there is architectural distortion in this region. We put the bars outside. It's very difficult to see anything there. Just cloudy, like the clouds we have now. There is nothing, no specific pattern. Even if you zoom, this is a part of the normal image. You see some parallel lines. In architectural distortion, it's very difficult to see where is the speculating pattern. So we need some enhancement, and we need a method to detect such patterns. And for this, we have used Gabor filters. We had many discussions with the radiologist, Dr. Desatel, and kept asking questions. What is important? Is it density? No. There is no variation in density. So what is important is the orientation. If in a region where you expect the breast tissue to go like this, if there is some tissue pattern going that way, that is distortion. So for that you need to know where in the breast you are looking at the patterns, and also which way the tissues are pointing. Now there is no movement of anything in the mammogram. It's only texture, but oriented texture. And for this, we extract the orientation field. At every pixel, there is a gradient measure to detect edges. But we don't want to detect edges, we want to detect tissue patterns. Tissue patterns with a certain thickness, not edges. And then for all such patterns of fibroglandular tissue, we want to get the orientation at every pixel. And that is possible by use of Gabor filters, and this is referred to as the orientation field. Now this could be noisy because of artifacts in the image and errors in the image processing algorithm, but the decision algorithm. So we filter and downsample the orientation field. To analyze the orientation field using what are called phase portraits, I'll explain this, to detect patterns that are converging or diverging, called a node pattern. We post-process and find these points identify them as suspicious regions of architectural distortion, analyze them further, and then detect sites of architectural distortion. A few equations. Gabor filter is a two-dimensional Gaussian. This is a Gaussian function multiplied with a sinusoid, cosine 2 pi fx. The Gaussian has two parameters, sigma x, sigma y, the width or the variance in each direction. The cosine has one frequency in the x direction. Now we have to relate these parameters to the patterns we want to detect. And the patterns are fibroglandular tissue. The fibroglandular tissue in the breast are in the range of 100 to 300 micrometers in thickness. So we say that is the thickness tau of the average pattern we want to detect. And breast tissues will go in a straight line for some distance and then change the direction. So for that we define a parameter called L. What is the length of the tissue before it changes direction in a relative manner? And then orientation theta. What is the orientation? Well, all orientation. 0 to 180 degrees or minus 90 to plus 90 degrees. If you want to operate in a narrower range for some other application, you could define a narrower range of angles. So F is 1 over tau, sigma x is tau divided by a scale factor, sigma y is L times sigma x, and then this Gabor filter, which is oriented in the, which is placed along the x-axis, can be rotated to any angle you want. This is just a geometrical transformation. So here is a Gabor filter oriented in this direction. So there is a main lobe which is positive. The Gaussian is a positive function, but it is multiplied with the sinusoid. So there is a main lobe and then a negative side lobe and a positive side lobe and negative. So it decays. It is like a bell that is pressed in one direction and stretched in the other direction. So this is what it looks like in the image domain. If you increase L, make it longer, it looks like that. If you increase the thickness, it is thicker. If you rotate, it is rotated that way. So if you use a function like this, it will detect patterns that are oriented in this angle. So if you have this pen here, this filter is a matched filter, it will detect this. If the object is sitting like this, none of these filters will detect. You need a double filter going this way. So you make a bank of this type of filters for all angles, 1 per degree, and filter the image. You can do that easily in the frequency domain. If you take the Fourier transform, these are the Fourier transforms or frequency response of the filters. They're all bandpass filters. This is zero frequency here, horizontal frequency, vertical frequency. This is a Gaussian. The gain here is 0. So intensity information is removed, low frequency information is removed, high frequency information is also removed, and information only in this band is passed. And when you rotate, information only here is passed. Everything else is rejected. So when you apply a bank of these filters, you get the output having tissue patterns in various directions. Now you want to detect tissues in all directions, so we say take the maximum of the outputs of all the Gabor filters at each pixel. That will detect all the oriented patterns. And then we also say the angle of that filter that gave the highest response. And that gives you the angle of the tissue pattern at that angle. So if I have a pattern like this, then I get the angle at that corresponding position. So here is a region with architectural distortion, zoom. So maybe you can see some spicules here, some oriented patterns. There is no tumor here. Gabor filters are like matched filters, line detectors. So we are getting the orientation. If you look here, there are some lines. These are the Gabor filter angles shown as straight lines. So there is a tissue pattern going like that, which agrees with what you see there. Now when there is architectural distortion in a small region, now mammogram has many patterns. Architectural distortion is only one small region, maybe 1 centimeter by 1 centimeter in the full mammogram, which would be 20 centimeters by 25 centimeters. So you have to analyze the mammogram using a sliding window, a small window. When the window contains a pattern of architectural distortion, you may expect, ideally, this kind of an angle or orientation field. Tissues radiating tissue patterns in all directions. Now this doesn't happen in a mammogram. This is an ideal mathematical situation. This is called a node. When the patterns are like this, it is called a saddle. When the patterns are going in a spiral, it is called a spiral. So this is what is called a phase portrait, and this is a set of orientations that indicates the possible movement of a particle under the influence of a vector of force field. There is a velocity field created which has two components, dx, dy, velocity in the x direction and y direction. And there is a linear model that says the velocity is related to the x and y coordinates in terms of the 2 by 2 matrix A and a 2 by 1 matrix B. So this is the model. And depending on the eigenvalues of this matrix A, you can decide if the pattern is this, or that. So in a mammogram, of course, there is no particle moving, but these could be treated as the orientation of the tissue at every pixel. So then, we use a small window, 41 by 41 pixels, for a mammogram that has 1000 by 1000 pixels after filtering and downsampling. So in this window, the question asked is, these are the angles given by the Gabor filters for the tissue patterns. Is that a node, saddle, or spiral? So you take these angles, put them through that equation that we saw, this equation, and then ask what is the matrix A that generated this pattern? Some values. What is the matrix B? So there are 6 parameters you have to determine given this pattern, this set of angle values. And we do that using optimization, nonlinear least squares optimization. We get these values. Then ask the question, what is this? Is it a node, saddle, or spiral? Get the eigenvalues of the matrix A, and if they are both real and positive, then it is a node. We are not interested in these, so we throw them out. So for every position of the window, you ask the question, is it a node? If it is a node, okay, where is the focal point of the node? The focal point of this node is here, but you may be analyzing the pattern here. So it says, yeah, this is node, but the focal point is here. And that is given by A inverse B. So by using that relationship, you can find where is the focal point, and at that focal point, we increment the value for every position of the window. So in this way, you generate this phase portrait map. And after you run the window of analysis over the entire image, the node map will have many votes. A large value here, which is the center of architectural distortion. The node, the saddle and spiral will have some values, but we are not interested. So as expected, this is a site of architectural distortion indicated by the radiologist. Center is here, and there is a large value there. So it works. But when you apply it to a full mammogram, it's not so easy. It takes a lot of computing time, no problem. By bigger computers, more computers. This is a mammogram. This is the site of architectural distortion given in the database. This is the magnitude response of the Gabor filters. All oriented tissue patterns are detected. This is the edge of the pectoral muscle. This is the nipple, where there is a converging pattern. So naturally, the nipple is a node. And this is the angle field, the orientation field. So breast tissue is converging, but in this part, you see breast tissue going in various directions, if you look at this part carefully. So that is a node pattern, very clear. And the node map has a large value here. So we looked at this and said, oh yeah, it is working. But then it's not working. It's giving many, many false positives. Why is this a false positive? Edge of the pectoral muscle and two intersecting patterns. They all have different planes. The pectoral muscle is everywhere, but there could be one ligament here, another ligament here, another blood vessel there, but they will all superimpose and cause this, which is a false positive. So we get this, but there are false positives. So with a small test set of 19 mammograms with architectural distortion from the Mammographic Image Analysis Society, MIAS database, we got a sensitivity of 84%, but 18 false positives per image. Now this was, we were very thrilled at this. Fabio Iris from Sao Paulo, he was working with me. This was his PhD project. We were happy, but we said, no, not a PhD yet. This is too much, 18 false positives per image. So let's go back and do a little bit more work. So we prepared these images and went back to the radiologist and asked, what is causing this problem? Why are we getting all these false positives? So here is the region of architectural distortion, and you don't see much there. There are so many intersecting patterns. So we analyzed such images with the radiologist, and the confounding structures were found to include edges of vessels. Gabor filter is a bandpass filter. It will detect also edges. If the thickness of the object is not matched to the size of the Gabor filter. Intersections of vessels or superpositions of vessels. One vessel here, another vessel somewhere else in the breast, and they superimpose in the mammogram. Edge of the pectoral muscle, edge of the fibroglandular disc, and these are all referred to as curvilinear structures. They are linear, and then they change curvature or orientation, and over the image they are not linear but curvilinear. So here is an example of a region of interest. There is a vessel here. This is the output of the Gabor magnitude, the edges of the vessel, and many other parenchymal patterns. And we apply a technique called non-maximal suppression to detect edges. And we said we will reject all these pixels. But then we lost sensitivity. A lot of information was thrown out. So then we applied another technique where we take the angle from the orientation field and the direction perpendicular to the gradient vector. So at every pixel we get the gradient and check the orientation. And if the difference between the two is less than 30 degrees, then we identify that pixel. Now these are the pixels that are retained for further analysis. So we reject many structures that would be corresponding to edges because we want to analyze only fibroglandular tissue. So here is a node map for a full mammogram without curvilinear structure analysis. This is after the analysis, and there are many false positives here. And by the way, PDF files of my presentation, this and the lectures in the afternoon will be given to Dr. Bhatti here, and you can collect, if you're interested, get them from her later, or you can go to my website. They're all available on my website. So then you can see the details a little more, because the projection here and the light, it is hard to see all the details. On my screen I can see there are many large values here, and also at the level, these are all reduced. But at the site of architectural distortion marked in the database by the radiologist, there is a large value. So if you detect local peaks in this image, you will detect this. And depending on your threshold, you may detect some other false positives. So this is better. So we did receiver operating characteristic analysis. Dr. Alicia explained this yesterday. But this is what is called FROC. In FROC analysis, you have the sensitivity of detection plotted against the false positive per image. Now, if you come here and say, I'll set a threshold and I can detect this. Well, sometimes this may not be the first or the biggest one. There could be something else like here. This may be number one. So if the radiologist says, I'll allow you to put 2 marks per image, then I may put number 1 here and number 2 there, so I'll detect architectural distortion. Not first, but second, maybe third. So how many marks will you allow me to put on the image before you say, that's too many, don't bother. So if you allow up to 5 false positives per image, previously we were getting a sensitivity of only 50%, but with this analysis we will go up to 60%. If you want 80%, then you have to allow about 7 or 8 false positives per image. Then your sensitivity of detection will increase. So next we ask the question, how can we improve it even more? And by looking into the model, we found another possibility. The matrix A, we put a condition that it must be symmetric. Then spiral is not allowed. We don't care. We don't want spirals. So we put a condition that it must be symmetric. There are only 5 values to determine by optimization. The eigenvalues are these. You can find the angle between the principal axis and the orientation field of this matrix is this. Could there be architectural distortion like this in a mammogram? Maybe. But mostly architectural distortion will have lines going like this, not shooting like this. So we said this is about the limit. If you go further, if the angle between the principal axis is 15 degrees, you get a pattern like this. Mathematically, this is a no. But this is not architectural distortion in a mammogram. In this one, the condition number is 20, and the patterns go like this. This is also a node, but we don't expect this in a mammogram. So the condition number of the matrix is a clue. So if the condition number is less than 3, we keep the result. More than 3, reject. So with the database of 19 cases of architectural distortion, including 41 control mammograms, normals from the MAIAS database, we put a condition the matrix A must be symmetric, the condition number must be less than 3, greater than 3 you reject. We got sensitivity of 84% at 4.5 false positives. So we reduced the false positive rate, maintaining good sensitivity. Now 84% is not very good, but it is better than what we had seen in the literature at that time. And we could go to 95%, but with 10 false positives, and I don't think anybody would want to see 10 marks per image. A radiologist may tolerate 1 or 2 extra marks. When you are assisting the radiologist will have to look at every mark you put and then analyze. But the radiologist can easily reject false positives. And a true positive will catch the attention of the radiologist. And if the cancer is detected, that is good. So with that, Fabio got his PhD. And then the next student came and said, I want to do work on this topic. And we said, well, it's already done. We want to do work on this problem, then we have to make it even more difficult. So now, for another project that Shomishta Pragna and her husband Shanti Mubani, both of them worked on this project, we made it more difficult. We said, we will not take mammograms on which cancer was detected by the radiologist. We will take those cases and we will go 2 years before in the screening program and get the previous mammogram, the last mammogram taken in the screening program before cancer was detected. And that is called screen-detected cancer. If cancer is detected in the screening program when a woman comes and she is found to have cancer, there will be previous mammograms if the woman has been in the program for a few years. So suppose cancer was detected in 1998 and the woman had been in the program for 10 years, 1996, cases will be, or films will be brought up. In any case, when a woman comes to a screening program, not all, but the previous set of mammograms will be given to the radiologist for comparative analysis to see what has changed. So in this study, we went to the prior mammogram of two types. One, screen-detected cancer, and another, even more difficult, what is called interval cancer. Women in the screening program are asked to come every 2 years. So suppose a woman has been in the screening program for 6 years. So 2000, this is 2015, so 2000, let's say 8 and 2010, 2012, 2014, next is 2016. But 2015 she feels something is wrong and goes to a clinic and cancer is detected. And in the cases that we got of such interval cancer cases, the cancer was detected outside the screening program. But with the registry of the province of Alberta, the information comes to the screening program. That this woman who was in the screening program went to that clinic and was diagnosed to have cancer. So we took those prior mammograms, the last fell in the screening program before cancer was detected. And unfortunately, we could not get the diagnostic mammograms, the images on which cancer was detected, because that was done outside. So Dr. Desatel read the clinical reports which were available and marked the suspicious regions of architectural distortion. So this is a set of prior mammograms. 1997, cancer was detected in this. This is 1 year before, 1996. So it's hard to see anything. This is the region with architectural distortion. So now the question is, what was there in the previous image 1 year earlier? Is there anything? Well, when you compare the two, you can draw this box. And Dr. Desatel drew this box and said, this is the suspicious region. But when this mammogram was interpreted in 1996, it was considered to be normal. Not by one radiologist, but by two, minimum 2 radiologists. There was no sign of disease. Or it was not clear enough. Later on, it was found to be clear. So we said, well, our methods can detect that. For the next student, I said, take these images and see if you can detect it. For that, this is the definition of interval cancer. Cancer where breast cancer was detected outside the screening program in the interval between scheduled screening sessions. So we prepared 106 prior mammographic images of 56 individuals detected with diagnosed with breast cancer. The time interval on the average is 15 months. And we also took 52, we call it prior mammogram in the sense, these are all normals, but we didn't take the last normal mammogram, but the one before. So these cases of normal breast were confirmed by one extra screening visit after that point. So here is an example. This is the region marked by the radiologist. You see some tissue patterns at various angles. Zoom and see the details. The angles are scattered. They are not oriented in any one particular direction. So this is part of the mammogram. This is the Gabor magnitude response showing the oriented tissue. This is the angle. And for this mammogram, for the whole mammogram, in the corresponding region in the node map, there is a large value. This is done for the whole image. So in this case, we said, we cannot simply use the node map because the false positive rate is very high. So we said, we will detect a number of peaks in the mammogram, not just number 1, but number 2, number 3, number 4, number 5, up to number 30. And we will cut regions all over the mammogram. If we find, sometimes we don't find 30 peaks, we may find only 10, only 20. But we said we will go up to 30. We don't want to miss anything in the first stage. So these are all the regions ranked according to the value of the node map. And this is number 1, right in the site of architectural distortion. But number 6 is here, number 2 is here, number 21 is also here. So we said we will take all of these and analyze them. Go through more feature extraction and pattern analysis. So far, the only feature is node value. Now we say we will get more features. These are some of the true positive regions. You can see some distortion, but sometimes there is nothing to see. False positives, some intersections of ligaments and vessels. These were all detected. So from these 158 images, we got 4,224 regions of interest, out of which 301 were true positives in the regions marked by the radiologist as architectural distortion. And these are all 3,923 were labeled as false. Now these regions cover almost the whole mammogram, which is okay. Now we do more feature extraction. Phase portrait analysis, will give you node value. We did fractal analysis, got fractal dimensions, angular spread of power using the Fourier transform, statistical analysis of texture using Haralick's method, which Dr. Leticia explained, and loss texture, and I'll explain some of this again in the tutorial in the afternoon. Then you go through feature selection and pattern classification, and classify all the regions and identify the true positives. So here is a region which is true positive according to the analysis by the radiologist. This is the Fourier transform. It is hard to see much there. We convert the Cartesian coordinates to polar, radial distance and angle. And we get, for all radial frequency, we integrate and we get a function of angle. This is the distribution of power here in terms of angle, 0 to 180 degrees. In case of architectural distortion, we expect a wide distribution. If it is a normal piece of tissue or normal part of a mammogram, then there may be only a few angles of power because of the presence of a few oriented patterns. And then we take the integral in this direction. So we get a function of radial frequency, a one-dimensional power spectrum from the two-dimensional spectrum. Now there is a model that is based on random walk and fractional Brownian motion, which says if the spectrum is decaying at a rate of 1 over f to the power of beta, when you plot on the log-log scale, there will be a linear portion, and the slope of this line will correspond to the fractal dimension based on fractional Brownian motion. So from this we get the fractal dimension. Then we apply loss texture measure, but I'll talk about this later on. Loss texture measure has a number of filters that are obtained by convolving smaller filters, and they can detect local average, edges, spots, ripples, and waves. In a mammogram, you don't expect ripples and waves, but when you transform, you can get some rippling patterns. So this is the result of loss operators detecting edges, spots, waves, and ripples. When you take the energy of these images, you can see various parts are highlighted depending on the pattern that is present there. So using the energy in these images, you can detect various patterns. In a mammogram, in the case of architectural distortion, which is shown here, we expect spicules going at various directions from the center. When you convert this to a polar coordinate system with the center here and the angle this going in the angular direction, this is the angle and this is the distance. And when you have a spicule, they will come as a vertical line here due to the transformation to polar coordinates with the center here. So if there are a number of spicules, there will be a number of lines, and that is a wave or a ripple pattern. So we apply the loss filter here. This is the R ripple filter, this is the wave filter. We get large energy values. We can detect architectural distortion in this manner by transforming. So here is an example of a true positive region, many directions of tissue patterns. And these are the angular distributions, fairly broad spread of angle using Gabor magnitude, Gabor angle, and we measured we obtained other measures of coherence and orientation strength, but these are not required. Only this is enough. In the case of a false positive region detected using node analysis, you don't see many angles, only one or two angles. So most of the angle distribution is here. So the entropy of this distribution after normalization will be small here and large here. In the case of architecture distortion, there is a broad spread of orientation strength or oriented patterns. So there is a big difference in this angular distribution from comparing a case of architecture distortion true positive region to a false positive region. So we computed several parameters of angular distribution, entropy, variance, and so on. And we use different classifiers, FLDS, Fisher, linear distinct analysis, Bayesian, and a feed-forward neural network using various functions, and we got area under the RSA curve up to 0.78, which is not bad. Note that all of these cases were considered to be normal at the time of screening by at least 2 radiologists. So to get 0.78 is a good result. The pre-response ROC curve showing sensitivity against false positive per image is this, which gives 80% at 5.8 false positives per image. Now this is similar to what we had earlier with mammograms, where cancer was detected by the radiologist. But now these are mammograms where the radiologist did not see any sign of cancer. We are getting similar 84% accuracy, sensitivity with 5-6 false positives per image. So this is a further advancement from the previous study. So Shantanu got his PhD for this. So this is the result of the classifier. The initial marking of all the regions. This is the region of architectural distortion. Unfortunately, number 24 is the site ranking by node map. After Bayesian analysis, number 1 is here, number 1 is here, number 2, number 3. All of these are false. The true region is here. This is a case where the method did not work. This is a case where it worked. Number 1 is there in node analysis. Number 1 remains there after all the features are calculated and the Bayesian classifier is applied. And these are the top 5, top 6. So you can decide how many you want to mark for the radiologist. Just 1. In this case it works, but not always. Maybe you should give 4, 5, 6, I don't know, maybe 3. That depends on the radiologist and the user, what the user can tolerate and analyze. We included further methods. I'm running out of time. I should finish. Do I have 5 minutes, 10 minutes? 15. Oh, okay, good. So we have, then we decided on analysis of dispersion of the power using some models. We said at each pixel we have a certain magnitude of the Gabor filter output. If the magnitude is high, then there is a specular. And then there is alpha. Alpha here is theta. Theta is the Gabor angle. And then we said we will assume that at the region of the window that was marked, at the center, if there is architectural distortion, if there is a spicule at this angle, at this point, this pixel which is on this spicule, the magnitude response of the Gabor filter must be large. The angle alpha 1 in terms of the geometry of the region must agree with the Gabor angle. The Gabor angle must be theta, and theta and alpha must be the same. If they are not, then it is wrong. It is not SPQ. So we said, multiply the magnitude with the cosine of the difference between theta and alpha. If theta and alpha are equal, the Gabor filter detected a real SPQ that is oriented at angle alpha or theta from the center of this region. And there is high magnitude response. So this is an index of convergence of SPQs towards the center of this region, if this is the region that was cut from the mammogram. So like this, we defined a few more. We computed radially weighted difference, comparing the image intensity at 2 pixels P and Q and the radial distance, and obtained this radially weighted difference. I don't have the time to go through all of this, so I'll skip some of these. And angle weighted difference, difference in 2 pixels along SPQ, potential SPQ, and the angle difference. If 2 pixels have similar intensity and same orientation, then that could be SPQ. And another measure of entropy. We compute entropy in angular bands and sweep this whole range and compare the entropy in one band to another band and check the difference in the angle between the two. And if there is large entropy and the angles agree, then there could be SPQs. So we put all of these, we analyzed all of them. When you have a number of features, there are various methods for feature selection, as we heard yesterday from Dr. Alberta. You analyze each feature, go through a feature selection algorithm. If you do principal component analysis, PCA, you can achieve dimensionality reduction, but you don't know which feature is helping you, which is not. So here we analyze every feature individually and ask what is its area under the ROC curve. Each feature can only give about 0.6, 0.7 if you are lucky. So they're all contributing a little bit, but not much. Any one of them will not be enough. So we put them through feature selection and training and cross-validation and various classifiers. So here are some results. I won't go through all of them. At 80% sensitivity, we got 5.3 false positives. Or if you're low 5.3 false positives, we can get 80% sensitivity. And we can get 90% sensitivity if you're low 6 false positives. In this case, false positives per patient for 2 mammograms, not per image. Because for each breast, there will be 2 mammograms. So this is the FROC analysis that indicates sensitivity of 80% at 5 false positives. I'll skip some of this review part and quickly mention another method that was developed by one of my PhD students from India. We went back to Dr. Dezical and asked, what about the region from where we get this rectangular part we cut? Suppose number 15 is here. Should we treat number 15 and number 5 the same way? And he said, no, they are different. The normal architecture here will be in this angle. The normal architecture here will be in this angle. So they are different. So based on that idea, we said we will try something else. Using the mammogram, we asked Dr. Dezical, can the mammogram give you an idea as to what is the orientation of breast tissue? He said, oh yeah, that can be done. And it is related to the curvature of the skin line. So for that, we then said, okay, this is the general idea. This is the expected loci of breast tissue. The ducts provide milk, and the milk has to go to the nipple, and all the supporting structures will have related orientation. And the breast outline will also have a corresponding orientation because the skin, of course, is containing all of this structure. So there is a relationship. So this will be the oriented texture in a mammogram as related to the anatomy. Now, how do you translate that to a mammogram? You have to find the breast boundary, and there are many algorithms. We have algorithms. You need to find the nipple. We have algorithms. There are many in the literature. Find the pectoral muscle. If it is mediolateral view, we can do that. So using this information, we said take that line, take the breast boundary, detect automatically, and we don't want to use the actual boundary. We fit a polynomial. This is a third order polynomial. This is just a second order polynomial. We cut the mammogram in parts using the nipple, the line perpendicular to the pectoral muscle straight line approximation. So this is one portion, this is another portion. And from this point we draw another contour that is derived from the breast contour there, and we call that region 1, region 2, and so on. Craniocaudal, we just draw a straight line, horizontal line at the nipple. This is superior part, and this is actually craniocaudal, that would be the medial part and the lateral part. There could be some small portions left out here. We treat them separately. And then we interpolate using the breast boundary as a reference and this as a condition of end of that. We get a set of contours going through every pixel. And similarly from here to this line, we get all these contours that are interpolated versions. And from here we get these interpolated contours all automatically. So these blue lines now give the expected normal orientation of breast tissue for a given mammogram. And then I'll skip these methods of interpolation. Then we said, does the angle detected by the Gabor filter agree with the angle given by the model? The Gabor angle is theta. The angle given by these blue lines obtained by the model are these. Are they equal? If they are equal, then that is a correct representation. Is the Gabor magnitude large at that point? And then normalize. Multiply the two. If they are equal, then the cosine value is large. Cosine of 0. And then we took 1 minus that. If there is disagreement, that is, there could be architectural distortion. So then we created a map of that and got the orientation. This is the orientation field using Gabor filters. These are the angles given by the Gabor filters. Compare with the other angles given by the model, and we get these maps. Then we have to analyze these for local peaks. And using local peaks here, we cut the mammogram into all these parts. And for all these parts, we compute all the features that I showed earlier, put through a pattern classification system. Got 80% sensitivity at 9.1 false positives per patient, not per image. And we tried this with many classifiers, many ways of training and testing, and the results I'll summarize at the end. With a combination of 86 features, including all these speculation features, Harrelix and loss texture features, 25 of them, angular entropy, spread, 15 Harrelix measures with angle co-occurrence. We also computed Harrelix gray level, well, it's not gray level anymore. Instead of using gray level at every pixel, we use the angle, Gabor angle, because orientation is important. So we use the co-occurrence matrices of angles and computed Harrelix measures. And we showed that they do better than grayscale. Angular dispersion, and then we did feature selection with stepwise logistic regression, Bayesian classifier and other classifiers with leave one out patient, leave one patient out. So leave one image out is leaving one image and training and testing. Leave one patient means all the images of the patient, all the regions of those small regions that are cut, they're all taken out, train the classifier and test with all of these images of the same patient. So with all these, the best result we have obtained so far is 80% sensitivity at 3.7 false positives per patient. So which is, I think, a good result. It is comparable to the results for the detection of masses in mammograms. Masses are very clearly visible. And these are using prior mammograms, mammograms taken before breast cancer was detected. So from all of these regions that are identified, in this case, number 6, number 8, and number 15, I think. They are in the region of interest, marked by the radiologist. After training and classifying, number 1 is here. It was number 8, then it became number 1. So in this case, all these others have been rejected. The false positives are here. Perhaps the radiologist can easily dismiss them and accept this. This is another example. The two breasts are two views of the same breast, craniocaudal and mediolateral. We did 2-view analysis, and number 1 is here, number 2 is here. So to conclude, our methods can detect early signs of breast cancer 15 months ahead of the time, because these are prior mammograms with a sensitivity of 80% and fewer than 4 false positives per patient. So this was the final result that we obtained, and we wanted to do more work. We said we can detect signs of architectural distortion with higher sensitivity and lower false positive rates. That's the aim. We could. And we also wanted to apply to direct digital mammograms and tomosynthesis images. With tomosynthesis, you get multiple planes, and the problem of superposition of structures that may cause false positives will be reduced. Unfortunately, we didn't get any grant to continue the work. So there is nothing more for me to report on this, but I believe this is a worthwhile result. So the project has been funded by these agencies, and Dr. Desertel is our collaborator in radiology, Dr. Mukhopadhyay from India, Naga Mudigonda, Hilary Alto, Fabio Iris, Shantanu Bonnet, and Jayashree Chakraborty, all of them did their PhDs on this project. And, Shavishna Pradna did her master's on this project. If you're interested in the PDF file of this and the tutorials I'll give later on, please visit this website. If you type in my name, Rangayyan on Google, you should be able to go to my webpage. You should be able to download this. Thank you for your attention, and if you have any questions, I'll try to answer.
Thank you very much. Really nice talk. I have a very quick question and then a more maybe easy one too, but I'm really curious. The first thing is how you showed that you cut that patches, that boxes, and you have some of them are inside the area detected by the radiologist, and you say that's a true positive and the other not. So the first quick question is just, what do you do when you have just like the 6? It's outside, it's in the middle. It's not completely inside the region. Not the 6. I'm sorry. Which one? 5. It's between the it's some part it's out, some part. How do you say it's a false positive or not? And how does it affect?
This is treated as a true positive because more than 50% of this is in the region, marked by the radiologist. Architectural distortion has no true boundary, and we ask the radiologist to mark rectangular boxes. So that is the constraint. So if a region that is obtained by this procedure of cutting the mammogram overlaps this box drawn by the radiologist by more than 50%, it is labeled as true positive. Or if the center of the box, this box is inside the region, it's the same thing. So it is overlap of more than 50%.
Okay. And then the question that I am more concerned is how sensitive is this method? For example, if you change the size of this boxes, I understand that you have to know the problem very well. You talked about how big are the, knowing exactly what you're looking at. which kind of subtle differences and everything, but I mean, if you change the size of the box, how is this going to affect your...
Yeah, so in order to compute, those are good questions and good points, which we have fortunately studied. We repeated these tests with different numbers of the regions. We said, what if I select only 10, 15, 20, 25, 30? We repeated. And we chose to take up to 30, could be fewer, up to 30 local peaks in the node map and get all these regions. They are overlapping, which is okay. So if you take only 10, the sensitivity will reduce because you may miss at the beginning. And once you miss in the beginning, you cannot get again. So it is better to have more false positives at the beginning, but have high sensitivity. The subsequent steps will only reduce false positives, will not increase sensitivity. No new region, if breast cancer was here, nothing will happen in further analysis. It was not detected at the beginning, and you will not get it later. So we want to have as many of these suspicious regions as possible. So we chose 30. We also tried different sizes, and they are related as to how big each of these yellow boxes is and how many of them. And if you make the boxes very small, you won't have enough data to compute the Fourier transform, fractal dimension, texture. So the box cannot be 16 by 16 pixels. That's not enough. It should be 64 square, 128 square, 250 square, 56 is too big. So we tried different sizes and different numbers, and then decided on this, which is up to 30, and these boxes are 128 square pixels. And the resolution at this stage of analysis is 800 micrometers per pixel, not 50. We start with 50 micrometers per pixel. But here we are analyzing the tissue patterns at 800 micrometers per pixel. So those are important questions. So to resolve the issue, we repeated all of this work using various parameters, and then I think we call them hyperparameters. Yeah. Through training and testing and evaluation of the final result, we decided on a certain set of these parameters.
Correct me if I'm wrong. Your work showed that there is a correlation between architectural distortion and the appearance of cancer in the future. What you can do with a patient that does not have cancer but have an architectural distortion? What is the procedure to do with this patient?
Yeah. It's a good question in the sense, what is architectural distortion? Is architectural distortion always cancer? No. There could be benign disease also causing architectural distortion. But all of the cases in our training set, they are from biopsy-confirmed cases of cancer. We did not have any case of architectural distortion without cancer. So now it's an important question, so you'll have to prepare a database including cases of architectural distortion without breast cancer. We don't have such cases here. And Dr. Desatel has told me that not all architectural distortion will become tumor. Some cases of architectural distortion may progress and develop to tumor. But if you can but most tumors, when they begin, will have architectural distortion. So if you can detect architectural distortion, you will catch tumors when they are just beginning. Now, whether a particular case of architectural distortion will develop into a tumor, we don't know. But most cases that have a tumor later will have architectural distortion at the early stages. So if you can catch architectural distortion and confirm it by biopsy, to check for malignancy, you have to put a needle and get biopsy. That's an accepted procedure. So if you can catch architectural distortion, benign or malignant, doesn't matter. And then do more tests, confirm with biopsy, and then take action. So this is not the end. Based on this, you will not send the patient for radiotherapy or mastectomy or anything. This has to be confirmed by more tests, including biopsy, and then action will be taken. But if you can detect architectural distortion of any kind first, you will catch many cases of cancer at a very early stage. That is what we are trying to show.